Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're dealing with a very simple problem, kind of introductory around the idea of a Carnot cycle, a heat engine, HE for heat engine, that is taking some energy, producing some work, and rejecting some heat, right? A heat engine needs to have all these components, right? That's kind of the definition. It needs to obtain energy from a source. That's what we call the hot source. It needs to reject energy to a cold source, to a sink, and then it outputs some work. So the idea here is we're going to try to find out what is the net work output, and also try and find out what is the source, the temperature of the source for this imaginary Carnot heat engine. This problem reads like so. A heat engine is operating on a Carnot cycle and has a thermal efficiency of 55%. The waste heat from this engine is rejected to a nearby lake at 15 degrees Celsius at a rate of 800 kilojoules per minute. Determine the power output of the engine and the temperature of the source. Okay, so this is problem 6.72. First thing I want to point out, whenever we see these kind of problems that talks about, sources, sinks, etc., we need to remember that it cannot be in Celsius, right? That's probably the main killer of students. It's right here. This has to be in Kelvin, all right? And we're going to look into the equation just in a second, but this has to be in Kelvin. Put a big star there, because whenever you see Celsius, remember to change. The next thing that comes to mind readily is that this guy is in kilojoules per minute. And you might notice that as I was reading, I paused there for a second, because this is definitely something to keep an eye out for, because we probably want to have this in kilojoules per second, right? So if I'm a student, I'm solving this, the first thing I'm going to do is highlight these two things, because they are odd. Okay, so the power output of the engine, that's what we need to find out. So if we're looking for power output, we're looking for something in watts, right? We want watts power. And then the temperature, this has to be something in either Kelvin or Celsius. Okay, again, because this is a source, I'm probably have it in Kelvin, but if you were to calculate it in Kelvin, transform it back to Celsius, that wouldn't be a problem. That would not be incorrect, right? So let's start with the basics. We have this heat engine here. It's taking in some energy, outputting some work, and we know its efficiency, right? We know its efficiency is 55%. What is the efficiency? Well, it's just a matter of how much we're able to output of what we want, right? How much I get of the things that I want, divided by how much I had to input, right? The total energy going in here. And you can check out a video that we did on a electric dam, right? A dam that was being used to produce electricity, hydropower plant, and that we talked about this concept and we applied this before. Okay, so in this case here, we know this is the general concept of efficiency. In our case, what are we looking for? Well, we're looking for work, right? This is what we want out of this. This is the work that the heat engine produces. What is the input? Well, it's all the energy that's going into the system, right? All the energy. Let's just put energy here for the sake of comprising it all. And all this energy, the energy that comes is the energy that comes from this guy here, right? So this little heat engine here that we can do a control volume around, is the balance around here is that we have some energy coming in, we have some energy that's going out, some energy out, and this energy is in the form of heat. It's being rejected, and we also have this work being outputted, right? Work net, that's what we work net, work out, right? So if you do a very simple energy balance here, thinking about the first law, we can't really create or destroy energy, so therefore these all need to be in balance. You can see that the total energy that we're putting into the engine will be equal to the energy being outputted plus the energy being rejected, right? You can see that. Okay, and we're not talking whether this is heat or useful or anything like that. This is just the pure energy balance. Joules has to equal joules, right? So in this case here, what's the total energy? Well, total energy is, as we just saw, the energy, the useful work output, and the work divided by the useful work output plus the energy being rejected, EQ out. Well, we happen to know this guy, we happen to know that guy there, and we also happen to know the efficiency. So if those two pieces of information, the only unknown that we're left with is the work, right? So we can calculate that quite easily by knowing these things. Now, I'm going to go ahead and convert. I'm going to go ahead and convert the 800. Let's change colors here. The 800 kilojoules per minute. I'm going to convert that into kilowatts because I think that's always a good idea. And I know that 1 minute is the same exact thing as 60 seconds. So this is a multiplication by 1, and I'm not changing anything. And the minutes go away, and I'm left with kilojoules per second. And I get this is 13.333 forever, right? This is kilowatts or kilojoules per second. Okay, so what I have here is an equation in which I know all the, I know everything except for the unknown that I'm looking for, which is amazing, right? So I'm saying that 0.55 equals my work divided by work plus 13.33. Okay, beautiful. Now so I just need to solve this, and it's as easy as that. So to do that, I'm going to send this, let's go downwards. So I'm going to say that 0.55 of the work plus the multiplication between 13.33 times 0.55, that's about 45. 0.45 is equal to the work. So therefore, work will be equal to 0.55 divided by 0.45 multiplied by, this makes more sense. Yep. Yep, that makes sense. Cool. So this is 0.55 work plus 13.33. Beautiful. All right, cool. So this is in kilojoules. This is kilowatts. So this sensor is also going to be in kilowatts, and I get 16.3 kilowatts. Okay, that's the answer. That's the amount of useful work being outputted by this heat engine. Okay, nice. What else? The next part is what is the temperature of the source. Okay, and for this one, you're going to need to know a bit about Carnot engine, and that, the efficiency is also limited, I should say, by the temperature of the source and the temperature of the sink. Okay, I always go with this version of it, and then I know that this has to be a value that is greater. So that's what I use to remember this every single time. So this has to be the sink here, and this has to be the source here. And this is the equation that has to be in Kelvin, right? This is one that has to be in Kelvin, and where a lot of people go wrong because they put here in Celsius. This is not going to work. This is not going to be absolute, and therefore this equation does not make sense. Okay, so if I'm using this in Celsius, I need to put the T of the sink, which I know is 15, right? 15 plus 273 to have this in Kelvin. And I'm dividing by the temperature of the source, which is what I'm after, by the way. And I know this has to be the efficiency of the heat engine, which I've always known to be 55%. Okay, if that's 55%, then I can invert this T source. This is just going to be 1 minus, let's just send this one to the other side. So this is just going to be 288. Okay, so this is going to be 0.55, 1 of my 288. So I'm going to invert this. Is going to be 288 over T source. That has to be equal to 1 minus 0.55, and this is 0.45. So therefore T source will just be 288 divided by the 0.45, which is 640 Kelvin, right? See, keeping the same units. Note that here, this has the units of Kelvin, this has no units, so the units are kept. So this has to be the temperature of the source for this given heat engine. Okay, so simple analysis, once again, just relating the idea of efficiency back to this simple Carnot cycle. Now, before we go, just another way to do this, right? Another way to, and this is the way that when I've solved this, it's the way that the logic that I used, okay, was the following. I knew from the start that the heat being rejected was 13.33. We calculated that from the beginning, right? So Q rejected. And I knew the efficiency was 55%. So I knew 55% was what was outputting my useful work, right? That was outputting my work. Right? If 55% was being outputted as work, then that means that automatically just 1 minus 55, 45% was being rejected. Okay, if that's the case, note that we have a little proportion here. And I can say if 45% is 13.33, then what is the work? Well, you just need to do the 55% of that, right? So really simply, it's just the 13.33 times the 0.55 divided by the 0.45. And that obviously outputs the same number we had before. Okay, so this is 16.33. Okay, so this is, another way to do it. This is probably, this is going to be preferred by some of you. Hope it helps. You can choose whatever. Both are mathematically the same thing. Just the way you think about it is a bit different. All right, so hope this helped you out. If you have any questions, as per usual, just plug them down below in the comment section. If this video was useful, considering liking it, and we'll talk soon.